Download this code from codegive.com, link in the description below. Heap exploitation strategies for Sudo EP09, a detailed tutorial with code examples. Sudo EP09, also known as CVE 2020-13156, is a heap-based buffer overflow vulnerability in the sudo command line utility. This vulnerability allows an unprivileged user to escalate to root privileges on vulnerable systems. Understanding how this vulnerability works and how to exploit it is crucial for both security researchers and system administrators. This tutorial provides a comprehensive overview of heap exploitation strategies applicable to Sudo EP09, complete with code examples to illustrate the concepts. We will cover 1. Vulnerability analysis, understanding Sudo EP09. 2. Heap fundamentals and exploitation techniques. 3. Exploitation strategy for Sudo EP09. 4. Crafting the exploit, code example. 5. Mitigation strategies. 6. Considerations and further exploration. 1. Vulnerability analysis, understanding Sudo EP09. The vulnerability lies in how sudo handles \escapes within command line arguments when processing the S and I options. Specifically, the code that validates and escapes command line arguments before passing them to the exec system call contains a bug. The bug the core issue is in the unscape function, or equivalent logic, within sudo. When a \ is encountered at the end of a string, it's treated as a continuation character, and the next character is skipped without proper bounds checking. This leads to reading beyond the allocated buffer. Furthermore, the \ escaped character is copied to the buffer, allowing for manipulation of the data. Triggering the bug to trigger the vulnerability, you need to pass a carefully crafted argument to sudo that contains a large number of \ followed by a single character, and ensure the argument is long enough to overflow a heap buffer. The S or I options are the most common entry points. Impact This heap overflow can overwrite adjacent heap chunks, potentially leading to control over function pointers, data structures, or other critical memory regions. By carefully manipulating the heap layout, an attacker can gain code execution with root privileges. 2. Heap fundamentals and exploitation techniques. Before diving into the specific exploit, let's review some fundamental heap concepts and common exploitation techniques. Heap memory management. The heap is a region of memory dynamically allocated during program execution using functions like malloc and free. Memory is allocated in chunks. A heap manager, like glibxtmalloc2 or gemalloc, tracks the allocated and free chunks. Chunk structure. A simplified view of a heap chunk includes previous size size of the previous chunk, if the previous chunk is free. Size size of the current chunk. The least significant bits may contain flags, example previous in use. Data the actual memory allocated to the user. In free chunks FD and BK pointers, forward and backward pointers in the doubly linked free list. Heap overflow. Writing beyond the boundaries of an allocated chunk, overwriting metadata, size, flags, FD, BK pointers, of adjacent chunks. Heap spraying. Allocating a large number of similar sized chunks to create a predictable memory layout. This helps increase the likelihood of landing an exploit payload in a desired location. House of lore. A heap exploitation technique used to corrupt the small bins in the glib heap, allowing for arbitrary memory writes. This involves manipulating the FD and BK pointers of free chunks to write to an arbitrary memory location when a chunk is allocated. *fastbin duplication * overwriting the fd pointer of a free fastbin chunk and then allocating the same chunk twice. This can lead to memory corruption and potentially code execution. *unlinking * removing a free chunk from a doubly linked list. Vulnerabilities can arise when the unlink macro is executed on a corrupted chunk, leading to arbitrary memory writes. *cache poisoning * if cache is enabled. Overwriting the fd pointer of a chunk in the cache, thread cache, to point to an arbitrary address. The next allocation of a similarly sized chunk will return the attacker-controlled address. 3. Exploitation strategy for Sudo EP09. The general strategy for exploiting Sudo EP09 typically involves the following steps. 1. Trigger the overflow * craft a long command line argument with many backslashes to cause the overflow in the unscape function. The S and I options are typically used for this. 2. Overwrite adjacent chunks * the overflow overwrites metadata of subsequent heap chunks. The primary target is to manipulate the size and previous _size fields of these chunks. 3. Heap grooming * carefully allocate and free heap chunks to create a specific layout. This is often done using heap spraying to increase the likelihood of the overflow landing in a predictable location relative to other crucial data structures. 4. House of lore, or other techniques by manipulating the size, previous _size, FD, and BK pointers of chunks, use techniques like House of Lore, or fastbin dups, or cache poisoning, to gain the ability to write to an arbitrary memory location. 5. Overwrite pseudo-ers policy * a popular target is to overwrite the pseudo-ers policy data structure in memory. This allows you to bypass authentication checks and execute arbitrary commands as root. Another, more direct approach, if possible given heap layout, is to overwrite the user_cmnd variable in sudo, pointing it to /bin/sh. 6. Gain root access * after overwriting the pseudo-ers policy, or user_cmnd, execute sudo again. Because the policy is now corrupted, you can bypass the authentication and command restrictions, allowing you to execute a shell as root, example sudo /bin/sh. 4. Crafting the exploit, code example. Here's a conceptual example of a C-based exploit for Sudo EP09. This is a simplified demonstration and would require significant tuning and debugging to work reliably on a specific system. Remember that exploiting vulnerabilities can be illegal. Only perform this on systems you own or have explicit permission to test. Explanation of the code ***. Payload ***, the core of the exploit. It contains a long sequence of backslashes followed by a character. The length of the backslash sequence and the overall size of the payload must be carefully adjusted based on the target system's heap layout. Heap spray * allocates many similarly sized chunks. This makes the heap more predictable. Adjust the number of sprays and chunk sizes according to your target. The B character is used for spray chunks. This is often done so the overflowed metadata lands in a spray chunk. Command * sets up the arguments for execv. The vulnerability is triggered when sudo parses these arguments. *execv executes the sudo command with the crafted arguments. Important considerations for the code example address space layout randomization. ASLR randomizes the base address of libraries and the heap. This makes exploitation significantly more difficult. To reliably exploit this vulnerability, you might need to leak memory addresses to bypass ASLR, which can be done via information leaks or other vulnerabilities. You may need to disable ASLR on your test system for reliable exploitation during development. This can be done using echo 0 sudo t/proc/sys/kernel/randomize_va_space. Don't do this on production systems. *heap implementation *. The exploit needs to be tailored to the specific heap implementation used by the target system, example glib-tmalloc2, gemalloc. The structure of chunks and the behavior of the allocator vary. *offsets The offsets to pseudo-ors policy or other target variables are architecture dependent and can change with different versions of sudo and glibc. You'll likely need to use a debugger, example GDB, to determine the correct offsets on your target system. *heap layout Understanding the exact heap layout and how the overflow impacts adjacent chunks is critical. Use GDB with tools like pwndbg or GEF to inspect the heap during execution. *error handling Real-world exploits include robust error handling to handle unexpected conditions. *debugging Debugging heap exploits is challenging. Use GDB with heap analysis plugins, pwndbg or GEF, extensively. Breakpoints and heap visualization are essential. 5. Mitigation strategies. Several mitigation strategies can help prevent or mitigate heap-based vulnerabilities like sudo ep09. *patching The most effective mitigation is to apply the official security patch released by the sudo developers. *ASLR Address space layout randomization ASLR makes it more difficult for attackers to predict memory addresses, hindering exploitation. *rel-row Relocation read-only Partial rel-row marks some sections of memory as read-only, preventing attackers from overwriting function pointers. Full rel-row offers more robust protection. *stack canaries Canaries are random values placed on the stack to detect buffer overflows. If a stack overflow corrupts the canary, the program will terminate. *safe heap allocators Using secure heap allocators that include features like double free detection and heap metadata protection can make exploitation more difficult. *input validation Thoroughly validating all user-supplied input can prevent many vulnerabilities, including buffer overflows. In the case of sudo ep09, proper handling of \escapes would have prevented the bug. *code reviews Regular code reviews can help identify and fix vulnerabilities before they are exploited. *least privilege Run processes with the minimum necessary privileges to reduce the impact of a successful exploit. *hardening compilers Compile using security features such as Fortify Source and Address Sanitizer, ASAN. 6. Considerations and further exploration. Reliability Achieving reliable exploitation, especially with ASLR enabled, requires significant effort and a deep understanding of the target system's memory layout and heap behavior. Modern mitigation techniques Modern systems often have advanced mitigation techniques, like control flow integrity, shadow stacks, SET, that can significantly complicate exploitation. Ethical considerations Exploiting vulnerabilities without authorization is illegal and unethical. Only perform these activities on systems you own or have explicit permission to test. Dynamic analysis tools Tools like Address Sanitizer, ASAN, and Memory Sanitizer, MSAN, are invaluable for detecting memory errors during development. Further exploration Heap internals Study the internals of different heap implementations, example glib-tmalloc2, gemalloc. Advanced heap exploitation techniques Learn about more advanced heap exploitation techniques like cache poisoning, House of Einherjar, and safe linking. ROP Return-oriented programming (ROP) is a powerful technique used to bypass certain security mitigations and gain code execution. *CTF challenges participate in Capture the Flag (CTF) competitions to practice your exploitation skills. Security research papers. Read security research papers to stay up to date on the latest vulnerabilities and exploitation techniques. This tutorial provides a solid foundation for understanding and exploiting heap-based vulnerabilities like Sudo EP09. Remember that mastering heap exploitation requires a significant investment of time and effort. Be patient, persistent, and always practice ethically. Good luck.